All right, then, we want to find the exact coordinates of the points on this curve at which the gradient of the tangent is equal to 8. Now, how do we find the gradient of a tangent? We need to differentiate, okay? So we want to differentiate this function here. And with this particular function, we have got one function divided by another function. So we need to use the quotient rule. So I'm going to call the function on the top u. So u is equal to x squared. The function on the bottom is v, so that's 1 minus 3x. And if I differentiate both of those, I differentiate u, I get 2x. And if I differentiate v, I'm going to get negative 3. Then I need to put this into the quotient rule. And what is the quotient rule? It is v du minus u dv, or vu prime minus uv prime, all over v squared. Now, one of the most common errors is that people get this thing the wrong way around. They write u dv minus v du. And the reason they do that is because that's the same order as most people learn the product rule, right? People learn the product rule as u dv plus v du. So I suggest that what you do is instead you relearn the product rule in this order, right? So you relearn it in the same order, so v du plus u dv. That way, when you come to the quotient rule, all you've got to remember is to stick a negative sign here. You don't have to remember to switch the order as well. Okay, so I think that's often quite a helpful thing to avoid making mistakes. Now, what I'm going to do is I'm going to substitute everything in. So v is 1 minus 3x, u prime is 2x, u is x squared, v prime is negative 3, and this is all divided through by v squared, so it's going to be 1 minus 3x all squared. I think it's probably a good idea just to simplify this expression. So we've got 2x minus 6x squared plus 3x squared. And of course, minus 6x squared plus 3x squared is just going to be minus 3x squared. So I think I'll just simplify that straight away. Minus 3x squared, all divided through by 1 minus 3x all squared. Now, what we're asked to do in this question is to find where the gradient of the tangent is equal to 8. So that's going to be when dy dx is equal to 8. So we're going to write that down. When y prime is equal to 8, then what we're going to get is 8 is equal to 2x minus 3x squared all over 1 minus 3x all squared. And we will multiply through by that denominator. So on the left-hand side, we're going to get 8, 1 minus 3x all squared is equal to 2x minus 3x squared. And I'm going to expand that bracket on the left-hand side. So 1 times by 1 is 1, 1 times by minus 3x is minus 3x, but we've got 2 of them, so it's minus 6x. And then negative 3x all squared is positive 9x squared. And that's going to be equal to 2x minus 3x squared. If I expand then the left-hand side with the 8, that's 8 minus 48x plus 72x squared is equal to 2x minus 3x squared. I'm going to add 3x squared to both sides then. 75x squared. I'm going to subtract 2x from both sides. So that's minus 50x. And I've got the 8 on its own. Now, given that we're asked to find the exact coordinates, it may well be the case that we will get surds. It could be. Most of you got calculators, and calculators have got functions that enable you to find the roots of these equations very effectively. And it's worth learning how to do that, by the way, if you haven't already learned. But before we do any of that, I think it's probably a good idea just to see if we can factorize this. Now, the way we're going to factorize, right, is we're going to want two x terms that are going to multiply together to give 75x squared. So that could be 25x and 3x, or it could be 15x and 5x. And we also want two numbers that are going to multiply together to give a positive 8. So it could be numbers like 2 and 4 or 1 and 8. So I'm going to try, I think, 15x and 5x there. And I think probably 4 and 2 would be my guess. So if I put negative 4 here and negative 2 there, let me just see if that's going to work. So 15x times by negative 2 is negative 30x, and a negative 4 times by 5x is negative 20x. So negative 30x minus 20x is negative 50x. So that all works. And that means we've got two solutions, right? Either 15x minus 4 is equal to 0, in which case x is equal to 4/15. Or we've got 5x minus 2 is equal to 0, which means that x is equal to 2/5. So these are the two x coordinates. But if we read the question very carefully, the question says find the exact coordinates, not just the x coordinates. We want to find the y coordinates as well. So the function is x squared over 1 minus 3x, right? So the function is y is equal to x squared over 1 minus 3x. So we can say that when x is equal to 4/15, y is going to be equal to 4/15 all squared over 1 minus 3 times by 4/15, which is going to be 4 upon 5, right? Because the 3 and the 15 will cancel off. And then when x is equal to, what was it, 2/5, then y is going to be equal to 2/5 all squared over 1 minus 3 times by 2/5, so that's going to be 6/5. And it'd be good practice to do a little bit of that in your head, but I think you could also just key it into a calculator since you've got them. So if I was to do that, then I would get y value of negative 4/5 and 16 upon 45. So this guy would be 16 upon 45. Okay. And the other one is going to be negative 4/5. Okay. Right, so our two coordinates are going to be 4/15 and 16/45 and 2/5 and negative 4/5. And those will be our answers. Okay, so here we are in question 2 on an Argand diagram. Shade the region whose points represent complex numbers satisfying these inequalities. Now, I think before you do this, it's always helpful just to kind of rewrite the inequalities in a way that's going to be helpful. So I'm going to start by doing this. We've got z minus 0 plus 2i is less than or equal to the modulus of z minus 2 plus I. Okay, and we've also got the argument of z minus 1 plus 0i. Now, the reason I write it like that is because these guys represent, these things here, represent kind of the center of where we're taking our loci from. So here we've got a center of 2i on the Argand diagram, and here we've got a center of minus 2 plus I on the Argand diagram, and here we've got a center of minus 1 plus 0i on the Argand diagram. So we always want to have everything in terms of z minus some complex number, and something that's really helpful to include 0 here, just to clarify what the real part is, even if there is no real part. Okay, now dealing with this guy, the way we want to deal with this inequality is basically want to find the perpendicular bisector connecting these two complex numbers here. So the way I'm going to do that is I'm going to start by drawing out an Argand diagram. Let's try to do it a bit better than that, I think. Do that and do that. Okay, and I'll make this, I don't know, 1, 2, 3, 1, 2, 2, 3. So we want a complex number there centered upon 0 plus 2i. That's that guy there, right? That's 0 plus 2i. And we've got another one, negative 2 plus I. So that's that guy there. So negative 2 plus I. So what we want to do is want to find the perpendicular bisector of the line connecting these 2 points. So we need to find the midpoint of those. Well, how do we find the midpoint? What we do is we add up the two real parts. So negative 2 plus 0 is negative 2. And then we divide through by 2. It gives us negative 1. So let me just write that down. So we've got negative 2 plus 0 divided by 2. And then for the imaginary part, we do add those up. So we get 1i plus 2i is 3i, divide by 2, 3 upon 2i. So let me write that again, 1i plus 2i divided by 2. Okay. So this gives me a midpoint of -1 plus 3 upon 2i, which is roughly here. Okay, so let's put that there. That's where our midpoint is going to be. Now, if you want, you could sort of roughly draw on the perpendicular bisector, but we'll try to do it a little bit more exactly. And I think the way to deal with that is just convert these to coordinate points, actually. This is the point on the diagram with coordinate -2, 1. This is the point on the diagram with coordinate 0, 2. We can find the gradient of that line. Okay, so we can find the gradient by saying this is equal to 2 minus 1 over 0 minus 2, which is going to be a gradient of a half. And we want a perpendicular gradient, right? So the gradient perpendicular is going to equal to -1 divided by a half, which is -2. So we've got a gradient of -2. And the line is going to go through this point here, the point -1, 3 upon 2. So we can use our equation for a straight line. So y minus y1 is equal to m x minus x1, so minus 1. If I rearrange that, I got -2x minus 2 times by plus 1 is -2. And we're going to add 3 upon 2. So -2 plus 3 upon 2 is -1/2. Okay. And so how do we interpret that? Well, we've got a straight line there with gradient -2 that goes through the y-axis at -1/2. So where's that going to be? That point's going to be there, roughly -1/2. So our line, which I guess I'll draw in green, our line is going to look something like that. Okay, that's the perpendicular bisector, sort of. And have I got that right? Yeah, okay, it looks okay to me. That looks right. Okay, so that's going to be our region there. Now, that satisfies the first inequality, or rather, not quite yet, because this is an inequality, isn't it? Right. So we want the region where this thing is less than that thing. So we want to be on this side of the Argand diagram. Well, where is that side? It's over here. So this region over here satisfies this inequality. Okay, so let me state it again. This perpendicular bisector is where this side is equal to that side, right? It's where it's equal. So we want to be not equal, we want to be less than or equal. So where is this side going to be less than the right-hand side? Well, we'd have to be nearer to the point 0 plus 2i. So if we're nearer to the point 0 plus 2i, we're going to be on this side of the line. So it's that part there. Okay. All right. Then the second part is the argument of z minus 1 plus 0i. Well, firstly, we're going to put on the point -1 plus 0i. That's there. Beg your pardon. Let's do that in red. And that guy is there. And we want an argument of 1/4. So I'll draw that on like that. An argument of 1/4 pi is going to look like that. Okay, and we want to be less than or equal to 1/4 pi, but also greater than 0. So an argument of 0 looks like that. So what region is that? Well, we're between these lines here. So we want to satisfy this region and also this region. So if we satisfy them both, then that's going to be, if I just shade in, let's make it nice and big, that's going to be this region here, that whole thing. Okay, that guy there. Okay, so I hope that's sort of a bit more clear. Let's just get that in. So that whole thing. Okay. Right, so I can't be here, because if I'm here, I don't satisfy the argument inequality, and I can't be in this little tiny region there, because if I'm in that tiny region there, I don't satisfy the top inequality. Okay, all right. Okay, then next question. The variables x and y are related by this equation here, where a and b are constants. The diagram shows the result of plotting ln y against x for two pairs of values of x and y. The coordinates of these points are this and this. use this information to find the values of a and b. Now, the question's actually got a graph on it, but you don't need the graph really to be able to solve this. What I'm going to do is I'm going to take this and I'm going to ln both sides. That's always really what you should do with these type of questions. So if we've got y is equal to ab to the power of x, I'm going to natural log both sides. So I get ln y is equal to ln ab to the power of x. Now, if I take the right-hand side, I can split it up using the log rules. That gives me ln a plus ln b to the power of x. Then I can use the log rules there. I get ln a plus x times by ln b. So what I've done is I brought that power of x, take that guy, bring it down to the front. And why have I done this? Well, basically because I then get the following thing. So I'm just going to rewrite this in a slightly different order. I get ln y is equal to ln b times by x, right, where ln b is a constant, plus ln a. Now, why is that such a good thing? Well, because this is effectively a y equals mx plus c graph, right? So in other words, what we're saying is, if we were to plot ln y against x, right? So in other words, I replace ln y with big Y there and a little x there with big X there, then I'm going to get a straight line where the gradient m is going to be the same as ln b, and the y-intercept c is going to be the same as ln a, right? And that's really the key thing, right? Is recognizing that if we were to plot x against ln y, we'd get a straight line where the gradient is ln b and the y-intercept is ln a. So I'm just going to write that down. That's the key thing, that the gradient m would be equal to ln b, and also that the y-intercept c would be equal to ln a. Okay, so basically what we want to do is we want to find the gradient and the y-intercept. Well, we've got 2 points, don't we? 1, 3.7. Write that down here. 1, 3.7. And we've also got the point, what was it? 2.2, 6.46. So 2.2, 6.46. Okay, so let's find the gradient of that. The gradient of that is going to be 6.46 minus 3.7 over 2.2 minus 1. Okay, and what would that value be? Okay, if I put that into calculator, I'd get 2.3. Okay, and then what can we conclude? Well, we can conclude that ln b is equal to 2.3. So therefore, ln b is equal to 2.3, and that means that b is equal to e to the power of 2.3. Okay, and we can put that into a calculator in a moment. Now, we want to find the y-intercept. Now, I think the best way to find the y-intercept is to just substitute it straight into here. So we can now write that y is equal to 2.3x plus c. So big Y is equal to 2.3 big X plus c. What we're going to do is we're going to substitute in the point 1, 3.7. So 3.7 is equal to 2.3 times by 1 plus c, and that means that c is going to be equal to 1.4. And of course, if we've got 1.4 is c, then if we go up, we remember that c is equal to ln a. So ln a will be equal to 1.4, and so a is equal to e to the power of 1.4. Okay, so basically we've got our two answers. A is e to the power of 1.4 and b is e to the power of 2.3. So what we would need to do is we would need to put that into our calculator, and that would give us a is 4.06. So let me just put that here. A is equal to 4.06. And what was b? B would be 9.97. Okay, so just go up. B is equal to 9.97. Okay, and those are our answers. Okay, then question 4. The complex number u is defined by this, where a is a real number. Express u in Cartesian form: x plus iy, where x and y are in terms of a. Well, and basically this means that we're rationalizing this, I guess. So the way we do that is if we've got 3 plus 2i over a minus 5i, we want to get rid of the imaginary number on the denominator. The way we do that is we take the denominator and we multiply it by its conjugate, right? So we multiply it by a plus 5i, because that means that the I terms are going to cancel off. Now, of course, in order to maintain equivalent fractions, whatever we multiply on the top, on the bottom, we must also multiply on the top. So we're going to multiply that by a plus 5i as well. So I'm going to do that, and I'm going to expand. So on the top, I'll get 3 times by a, which is 3a, plus 15i. I'm going to get 2i times by a, which is 2ai, and I will get 2i times by 5i, which is 10i squared. And on the bottom, just do it in the long way, I think, what I'm going to get is a times by a, so that's a squared, a times by 5, so that's plus 5ai, minus 5i times by a, so that's minus 5ai, and then minus 5i times by positive 5i is minus 25i squared. Now, hopefully what you see is we've got those two terms are going to knock off. They cancel each other out. And also what we should be able to see is that the terms where we've got I squared, so I squared, those will be equal to -1. Why is that? Well, because I is defined as the square root of -1. So if we square it, then we'll get -1 there. Well, let's just simplify then. So we're going to get 3a, 15i plus 2ai. So I'm going to write that as bracket 15 plus 2, let's get rid of that, 2ai. And 10 times by -1 is minus 10. And then on the denominator, we have got a squared. Negative 25 times by -1 is going to be positive 25. So we get a squared plus 25. And lastly, if I was just to simplify this, then I'm going to get 3a minus 10 over a squared plus 25 plus 15 plus 2a over a squared plus 25i. Right? So in other words, this guy here is the real part, and this guy here is the imaginary part. Okay, then part B of this question, given that the argument of u is equal to pi by 4, we want to find the value of a. Well, I think it's maybe helpful just to quickly visualize what's going on. If we've got an argand diagram like this, right, where hopefully you remember that the x-axis is the real axis and the y-axis is the imaginary axis, then if what we've got is a complex number with an argument of pi by 4, the argument is the angle that the complex number makes with the positive real axis. In other words, it's that angle there. So what we're being told is that this angle is pi by 4 radians, which is the same thing as 45 degrees. Now then, if we've got a complex number in Cartesian form, right, so here we've got a complex number x plus iy, then that means that that coordinate there is x, and that coordinate there is y. But more importantly, from the point of view of the triangle, this length here is x, so that length there is x, and this length here is y. So what we could do is we could use our understanding of trigonometry to say that tan pi by 4 must be equal to the imaginary part, the y, divided by the real part, the x, right? Because tan is opposite over adjacent. So now if we go back to our complex number, our imaginary part was this thing, 15 plus 2a upon a squared plus 25. So I'm going to write that down. What was it again? 15 plus 2a. 15 plus 2a divided by a squared plus 25. And then divided through by the x-coordinate, which was 3a minus 10 over a squared plus 25. And if you key tan pi by 4 into your calculator, what you will get is you'll get 1. Okay. Now then, what we can next do is we can cancel off the a squared plus 25, right? Because we multiply top and bottom by a squared plus 25. Okay, and then if we were to simplify that, that means that what we've got is 1, beg your pardon, 1 is equal to 15 plus 2a over 3a minus 10. So if we multiply both sides by 3a minus 10, we get 3a minus 10 is equal to 15 plus 2a. I'm going to subtract 2a from both sides, so I get a. If I add 10 to both sides, I get 25. So my answer for a is 25, and I think that's all we're asked to do. Yeah, that's it. Okay, so here we are in question 5, which is a trigonometric question, and hopefully you should really notice that since we've got sine something plus something and cos something plus something, we're going to have to use the compound angle identities. And so I think it'd be very helpful if you immediately open up your formula book for your exam and just get those right in front of you so you don't make a mistake. I've reproduced them here. And instead of dealing with this as one big long equation, I think it's just easier just to split it up, to be honest. So that's exactly what I'm going to do. I'm going to take each term in full. So sine x plus pi by 6 is the first term. What identity am I going to use there? I'm going to use this one. So I'm going to get sine x times by cos pi by 6 plus cos x times by sine pi by 6. And if I was to simplify that, well, cos pi by 6 is root 3 upon 2. So that's root 3 upon 2 sine x. And sine pi by 6 is a half, so that's plus a half cos x. Okay, so that's the first term. Then I have to do sine x minus pi by 6. So sine x minus pi by 6. Again, what I could do is I could use the formula, but hopefully you should notice that actually the only thing that changes here is that positive is going to become a negative sign. And so what's going to happen is that positive there is also just going to become negative. So you can kind of skip a step if you want. That becomes root 3 upon 2 sine x minus a half cos x. Okay, so we kind of make our lives a little bit easier. Okay, then the next thing we're going to do is cos x plus pi by 3. So let's do that. So cos x plus pi by 3. And again, what we're going to do is just going to substitute that into the formula. So this becomes cos x cos pi by 3 minus sine x sine pi by 3. And of course, again, like pi by 6, pi by 3 is a critical angle. So cos pi by 3 is a half. So we're going to get a half cos x minus, and sine pi by 3 is root 3 upon 2. So it's minus root 3 upon 2 sine x. And again, if we do cos x minus pi by 3, then the only thing that's going to change is that negative sign in the middle, right? So this guy, instead of being negative, is that guy is going to become a positive if we just check the formula. So what we can do is we can repeat this thing here, but change that negative into a positive. So that's what I'm going to do again. So I'm going to get a half cos x plus root 3 upon 2 sine x. Okay, then we should be able to simplify all of this, right? So on the left-hand side, we're going to, of our equation, we're going to have this guy minus that guy, okay? And on the right-hand side, we're going to have this guy minus that guy. Well, let's just think about it. If I take this guy and I subtract this guy, then the 3 root 2 sine x, that thing, minus 3 root 2 sine x is going to cancel off. And on this side, we're going to get a half cos x minus a half cos x, which is plus a half cos x. So the left-hand side, we're just going to get cos x. Okay, so we get cos x on the left-hand side. Now, if we think about the right-hand side, if I do this thing and I subtract that thing, well, I'm going to get a half cos x minus a half cos x, which is 0. And I get minus root 3 upon 2 sine x minus root 3 upon 2 sine x. That's minus 2 root 3 upon 2 sine x, which is the same thing as minus root 3 sine x. And then the question asked me to find everything in terms of tan. Well, the way I can do that is I can divide left and right-hand side by cos. So on the left-hand side, if I divide by cos, I get 1. On the right-hand side, I'm going to get sine divided by cos, and sine divided by cos is tan x, sorry. So I'm going to divide both sides now by negative root 3. So tan x is equal to negative 1 upon root 3. And it's usually a good idea to rationalize. So the way we're going to rationalize is we're going to multiply top and bottom by root 3. So what we're going to end up with is minus root 3 upon 3. And that should be our answer. All right, then, so here we are in part B. Hence, we want to find the exact roots of the equation. Now, the word hence is a key thing, right? Hence means we need to refer back to our previous question, right, up here. So what we're really being asked to do when we're asked to find the roots of this is to solve tan x is equal to this. So we're solving this guy here. Tan x is equal to negative root 3 upon 3. Now, I'm sure you could do this by using your calculator and just adding pi and adding pi. I know many of you are just used to that, but what I want to do is just want to quickly explain this, if you don't mind, a bit more thoroughly. And the way I'm going to do that is I'm going to draw the graph of tan. Now, the graph of tan, right, it's got asymptotes at pi by 2 and minus pi by 2. So minus pi by 2, pi by 2. Because the wave repeats every pi radians. Okay, so if I was to draw out the tan graph, that would be my asymptotes there. Sorry about that. And there. And there. That's not too great, is it? Just make sure it goes through that. And the tan wave kind of looks like this guy. Try to get it right. Like that, like that, like that, like that. And then it repeats every pi radians. So like that, like that, like that. Okay, now if we're therefore trying to solve tan x is equal to negative root 3 upon 3, what we're really being asked to do is to find the intersections of this curve with the line y equals negative root 3 upon 3. So that's the line y equals negative root 3 upon 3. So we're being asked to find the intersection of that green line with that tan curve. And so if we use our calculator, what we're going to do is we're going to get that point there, and that point there is minus pi by 6. But the thing is, right, there's another solution here. And where is that solution? Well, it's one wave along. That's really the key idea, right? So these 2 points are like equivalent points, just on different waves. So if I want to go from this point here to that point, what I've got to do is I've got to move one wave along, which means I've got to add pi. And the equivalent thing can be said, right, if I want to go to the next wave, so let's say I wanted to do that, what I'm going to do is I'm going to move to the next wave like that. And again, I add pi radians. So my solution is going to be x is equal to negative pi by 6, but I can't have that because the domain that I'm asked to do is between 0 and 2 pi. So I can't have this solution. But if I add pi, I get 5 pi by 6, which is acceptable. And then if I add another pi, I'm going to get 11 pi by 6, which is also acceptable because it's less than 2 pi. So I think understanding the graph will really help you to get this question right. And in particular, it will help you to get the extra solution, 11 pi by 6, which I suspect a lot of students are going to miss. Okay, question 6. The parametric equations of a curve are given by this, and we want to obtain a simplified expression for dy dx in terms of t. Now, I think basically the key thing to understand here is we've got connected rates of change using the chain rule. So if I was to write, for example, dy dt, that's going to be connected to the rate of change for x, dx dt. And how is that? Well, through dy dx. Now, why is that? Well, you can kind of imagine the right-hand side here as being fractions, right? They're not really, but you can imagine it. And if you thought that way, then you could see that the dx's here are going to cancel and leave you with dy dt. Okay, so that's kind of the core idea that you need to understand, that you can find dy dx by finding dy dt and by dx dt, and then connecting them using this form here. Okay, now then, let's find dx dt. So if x is equal to t to the power of a half plus 3, by the way, I suggest you write in indices form. I think it's very helpful. Then dx dt is going to be equal to a half t to the power of minus a half. and then 3 differentiates to give 0. And if y is equal to ln t, then dy dt is going to be equal to 1 upon t. And so therefore I can just substitute this into the expression I've got on the top. So dy dt, which is 1 upon t, is equal to dy dx times by dx dt, which is a half t to the power of negative 2, negative 1 upon 2, which is 1 upon the square root of t, right? So a negative power means you do 1 divided by, and the half means that you've got a square root there, okay? So then what could I do? Well, I want to simplify, right? So I'm firstly going to multiply both sides by 2. So on the left-hand side, I'm going to get 2 upon t, and I'm going to multiply both sides by the square root of t. So multiplied by square root of t, I've got t to the power of half, I guess. And t to the power of half divided by t, we can use the indices rules. So for those of you a little bit less confident, a to the power of x divided by a to the power of y is a to the power of x minus y, right? I subtract the powers. So I've got power of half on the top, power of 1 on the bottom, and a half minus 1 is minus a half. So this is 2t to the power of minus a half. And again, for the same reason, that is the same thing as 2 divided by the square root of t. Okay, so our expression for dy dx is 2 divided by the square root of t. All right, then part B, hence find the exact coordinates of the point on the curve at which the gradient of the normal is equal to -2. Well, in order to understand this, we need to know that the gradient of the tangent times by the gradient of the normal is equal to -1, right? That's a key fact. Why is that? Well, because if two gradients are perpendicular, their product is -1, and tangent and normal are perpendicular by definition. So in this case, the gradient of the tangent is equal to -1 divided by -2, which is just equal to positive a half. So that's kind of the first thing we need to know. The second thing we need to know is that the dy dx tells us the gradient of the tangent. So this thing is our value of dy dx at a certain point of x, which we're trying to find. So what we're going to do now is we're going to set that a half equal to this thing here, 2 upon the square root of t. So a half is equal to 2 upon the square root of t. So if we cross multiply, we're going to get root t is equal to 4, which means that t is going to be equal to 16. And what we're asked to do is we are asked to find the exact coordinates. So our x value was the square root of t plus 3. So x is going to be equal to the square root of 16 plus 3, and the square root of 16 is 4, plus 3 is 7. And the y coordinate was given by, I think it was ln t, wasn't it? Ln t, yeah. So ln 16. And you might want to write that as ln 2 to the power of 4, and then hence 4 ln 2. And so therefore the coordinates are going to be 7, 4 ln 2, or ln 16. Okay, so here we are in question 7. The variables x and theta satisfy this differential equation here. It is given that x is equal to 1 when theta is 0. We want to solve the differential equation, get an expression for x squared in terms of theta. Okay, now the way we do this is with separation of variables. Separation of variables means we've got to bring all of the x terms to one side and all of the theta terms to the other side. So what I'm going to start by doing is multiplying both sides by tan theta d theta. I'm sort of treating that thing like it's a fraction. And if I do that, then I get x times by dx is equal to x squared plus 3 times by tan theta d theta. Okay, and then I'm going to divide both sides by x squared plus 3. So on the left-hand side, I get x over x squared plus 3 dx is equal to tan theta d theta. So can you see here, what I've got is I've got all the x's on one side, all of the thetas on the other side. And since that is the case, what I can now do is I can integrate both sides. So I'm integrating the left-hand side with respect to x and the right-hand side with respect to theta. Now, in order to integrate this, I need to recognize a form of integration. And that form is that if I have got, let's just go over to the right for a second, if I have got the integral of f prime x over f of x dx, then that integrates to give the natural log of f of x. Okay, the natural log of f of x plus c. Now, what that means is if you spot an integral where you suspect that you've got a fraction, and in that fraction, the numerator is the derivative of the denominator, right? So in other words, if you've got a function on the denominator that when it's differentiated gives you the numerator, then what you're going to get is you're going to integrate up to give a natural log, okay? So if you spot this thing, f prime x upon f of x, it integrates to give ln of f of x. Now that's the case here, because if you think about it, if I was to differentiate x squared, I'm going to get 2x. And that's very similar to that thing there. So what I'm going to do is I'm going to rewrite the left-hand side as the integral of 2x upon x squared plus 3 dx, just to make that very clear. But of course, if I've multiplied on the inside by 2, I need to divide on the outside by 2, right, to maintain the equivalent fractions. So just to be clear, the reason why I've rewritten it like that is to get it explicitly in the form where I've got f prime x over f of x, right? In other words, this thing is the derivative of that thing. Now, on the right-hand side, it's a bit harder to see, but we need to remind ourselves that tan theta is the same as sine theta upon cos theta. So we've got sine theta upon cos theta, and this guy is also in the form of f prime x upon f of x, because if I was to differentiate cos, I would get negative sine. So I just need to amend this integral as well. I'm going to make that negative sign on the inside, which of course means I've got to make it a negative on the outside in order to maintain equivalent fractions. So now that we've got this, we can use our rule and say the left-hand side is going to integrate to give a half ln x squared plus 3. And the right-hand side is going to integrate to give minus ln the cosine of theta. And of course, we need to remember with indefinite integration that we are adding a constant c. So the next step is to find that constant c, and we're told that when x is 1, theta is 0. So we're going to substitute that in. When x is equal to 1, theta is equal to 0. And therefore, if I substitute in, I'm going to get a half ln 1 squared plus 3, which is 4, is equal to minus ln cos 0. Now, cos 0 is just 1 plus c. And hopefully you recognize that ln 1 is 0, right? Because anything to the power of 0 is 1. So we're left here with c is equal to a half ln 4. And of course, we can say that that's the same as ln 4 to the power of a half by using the logarithm rules. And 4 to the power of a half is 2 because it's the square root of 4. So that's ln 2. So now that we got c, we can rewrite out our equation. We're going to get a half ln x squared plus 3. So a half ln x squared plus 3 is equal to ln minus ln cos theta, do beg your pardon, minus ln cos theta. And then we've got to add our c, and our c is ln 2. Okay. All right, then. How can we deal with this? Well, on the right-hand side, what we've got is we've got ln A minus ln B, right? That's one way we can think about it, right? If I was just to reverse this order, I could rewrite this as ln 2 minus ln cosine theta. And of course, if I've got ln A minus ln B, that's the same thing as ln A over B. So here I've got ln 2 over cos theta. Okay. Then on the left-hand side, a half ln x squared plus 3, well, I could use another logarithmic rule and write that as ln x squared plus 3 to the power of a half. Right? So in other words, I take that coefficient of the ln and I bring it up as a power. Well, if that's the case, then the two arguments of the lns here, right, this thing, x squared plus 3 to the power of a half, and this thing, 2 upon cos theta, they must be equal. So I can write this as x squared plus 3 all to the power of a half, or if you prefer square rooted, is equal to 2 upon cos theta. And therefore I can square both sides. So I get x squared plus 3 is equal to 4 upon cos squared theta. And therefore x squared is equal to 4 upon cos squared theta, or if you prefer 4 sec squared theta, minus 3. Okay, and that should be our answer. I'm just going to check the mark scheme just to see if that's right. Okay, the mark scheme gives it as 4 upon cos squared theta, right? But it says it'll accept the equivalent, right? 4 sec squared as well, because it's the same thing, minus 3. Yeah, so that's the right answer. Okay, then question 8, by sketching a suitable pair of graphs, show that this equation has only one root. Well, basically what we do is we sketch the graph of root x and we sketch the graph of e to the x minus 3, and we should hopefully be able to see there's only going to be one intersection point of those two graphs. Now, let me just start with the graph of e to the x, right? So hopefully you should know that the graph of e to the x looks like this. It goes through the y-axis at 1, and it's got an asymptote on the x-axis. So that graph is going to look, sorry about that, it's going to look something like this. So what's the graph of e to the x minus 3 going to look like? Well, it's the whole thing shifted down by 3, basically. So the y-intercept, if it's shifted down by 3, goes to negative 2. So you go down to there and there. So that would be negative 2 there. Let me just extend that line a tiny bit. Okay, and the asymptote, instead of being the line y equals 0 or the x-axis, it's going to be the line y is equal to negative 3. Okay, and so that's going to be like our new asymptote. So I'll draw that on in red. So that line, oh, that's not very good, is it? Let me just draw that on. That will be the line y is equal to e to the x minus minus 3. All right, so we just label that. That's like that. Okay, so that's the graph y equals e to the x minus 3. And what's the graph of root x going to look like? Well, the graph of root x just looks like this, starts at the origin. It's kind of like the quadratic, but on its side. It's like that. And remember, we only take the positive value of the square root in order for it to be a function. And then hopefully what you can see is that these graphs intersect at only one point. And they can only intersect at one point, right? Because this exponential graph is never going to come back down. And this root x graph is just going to keep going on and on that way, right? So in order for there to be another intersection point, what would have to happen is this exponential would have to come back down and cross over again, and that's just not possible. So what you want to indicate basically on your graph is there is only one intersection. Okay, like that. All right, then, part B of this question, we want to show by calculation that this root lies between 1 and 2. Now, how can we think about this? Well, let's say this is our root, right, the point of intersection. So let's say the point 1 is here. No, it's not quite to scale. Let's say point 1 is there and the point 2 is there, right? Then what are we going to notice? Well, on the left-hand side, the graph of the square root is going to be above the graph of the exponential. And when x is equal to 2, the opposite is going to be true, right? The graph of the exponential is going to be bigger than the graph of the square root. Okay, so that's what we basically need to show. And so we're going to do that. So when x is equal to 1, the square root of x is equal to 1. But e to the power of x minus 3, what's that going to be equal to? Let me calculate that. Okay, that gives me negative 0.28. Hang on, was that right? Did I read that right? Yeah, that was right. Okay, so what do we notice? We've got what we expected, which is the square root is greater than this. Okay, so we could write that like that. So therefore, the square root is greater than the e to the x minus 3. But when x is equal to 2, what are we going to get? Well, the square root of 2 is equal to 1.41. And then e to the power of 2 minus 3 would be equal to what? Let's put that in. Okay, that's 4.39. And in this particular case, what do we see? We see that the square root of x, or the square root of 2, is less than e to the 2 minus 3. Okay, so e to 2 minus 3. So I'm just going to actually change this thing I did just a moment ago. Let me just make that more clear. Yeah. Right, so square root of 1 is greater than e to the 1 minus 3. And if this is the case, right, then what's happened is we've had a change, right? The square root graph has been greater than the exponential graph, but in this case, the square root graph is going to be less than the exponential graph, and so therefore we can conclude. So therefore, there must be an intersection at this point. Now, that's one way of doing it. But I think probably a better way is as follows, right? So we're asked to solve square root of x is equal to e to the x minus 3. And if I were you, what I would do is I would bring one side to the other. So I would rewrite this as the square root of x minus e to the x minus 3 is equal to 0. So that's how we're going to find the roots. And what would happen if we substitute in x is equal to 1? Right, then what we're going to get is we're going to get either a positive number or a negative number. And if we substitute in x is 2, we'll get either a positive number or a negative number. And the key thing is, right, if the sign changes, if we go from negative to positive or positive to negative, then what we know is that we must have gone through 0. Okay, so if I substitute in x is equal to 1, I'm going to get 1 minus the thing that I had before, right, which was negative 0.28. 1 minus negative 0.28, and that is equal to 1.28. And the key thing about that is it is positive. But when x is equal to 2, I've got the square root of 2, which was 1.41, minus, what was the other one? 4.39. And actually, I don't really care what that value is. The only thing I really care about it is negative, right? So the point is, right, since there has been a sign change, right, then there must be a root between x is equal to 1 and x is equal to 2. And I would strongly encourage you to use that second method, right? In other words, bring one of the functions to the left-hand side, substitute in your values, and see if you've changed from positive to negative or vice versa. That can also be a very useful thing with other questions that are a little bit more complicated. Okay, then part C of this, show that if a sequence of values given by this iterative formula converges, then it converges to the root of the equation given in A. Now, look, guys, what does convergence actually mean? If we've got convergence, then it means that xn plus 1 is eventually going to be equal to xn, where n is large. Okay, so where n is large. In other words, if we ran this iteration like 100 times, basically x of 101 should be the same as x 100. And that means that we can replace this iterative formula with just x is equal to ln 3 plus the root of x. Okay, and therefore, if we convert that, we get e to the x is equal to 3 plus root x. And of course, rearranging that, the root of x is equal to e to the x minus 3, which is the same as the equation given in part A. Now, I think in the mark scheme, it doesn't actually require you to state this, but I think it's very important that you understand it, right? This is the key idea, actually, that convergence means that the two consecutive terms are basically going to be the same as each other, okay? Okay, then, final part of this question. Use the iterative formula to calculate the root correct to 2 decimal places. Give the result of each iteration to 4 decimal places. Well, we're going to start, I think, with x0 is equal to 1, because in the previous part of the question, we were told that the root was between 1 and 2, so that seems like a sensible place to start. And then we basically need to know how we can key things into the calculator intelligently. So what you want to do on your calculator is you want to press 1 is equal, because then what that's going to do is it's going to store it as the answer. So you're going to store it as the answer. like that. So I'm going to do that. 1 equals 2. And then what you want to key into your calculator is the following. You want to key in ln bracket 3 plus the square root of answer, like that, close bracket, and then hit equals, because then what's going to happen is the result of that is going to be the new answer, which means that you can keep hitting equals and you can get all other subsequent roots. So that's what we're going to do. Okay, so I've done, I'm going to do that now. So ln bracket 3 plus the square root of answer, close bracket, equals 2, and that gives me 1.3863. Okay, so we want it to 4 decimal places. Okay, now all I've got to do is I just got to hit the equals button again to get x2. And if I do that, I get 1.4297. 1.4297. Hit the equals button again. I get x3 is 1.4341. And then hit the equals button again. I get x4 is equal to 1.4345. 1.4345. And I'll hit the equals button again, x5, right? And that's 1.4345. Okay, and if I was to hit it again, I get 1.4345, and you just keep hitting equals, right? Well, keep going, keep going, keep going, keep going. There's no change, 1.4345, and we were asked to do it to 2 decimal places. So to 2dp, the root is x is equal to 1.43. Okay, all right, I hope that was helpful. Okay, then, question 9. The diagram shows the curve x e to the minus quarter x squared, and its maximum point is here at m. We want to find the exact coordinates at m. Well, a maximum point is where dy dx is equal to 0, because it's where the gradient is equal to 0. If you just think about that, if I was to draw the gradient, the tangent there, that gradient is horizontal, so it's 0. Okay, so what we want to do is we want to differentiate our function. Now, what do we got here? We've got one function, x, multiplied by another function, the exponential. So when we've got one function multiplied by another function, we have the product of two functions. And when we've got the product of two functions, we need to use the product rule. So I'm going to set u is equal to x. I'm going to set v is equal to e to the minus a quarter x squared. I've got to differentiate both of these guys. So if I differentiate x, I get 1. That's kind of easy. If I differentiate the v, well, the way we differentiate an exponential is we take the power, we differentiate it, and we stick it at the front. So if I differentiate minus a quarter x squared, I get minus 2 quarters. And then I'm going to get minus 2 quarters x, beg your pardon. And then I multiply it by e to the minus a quarter x squared. So let me just explain that again. I take that power, I differentiate it. So the 2 comes down to the front, minus 2 upon 4. Subtract 1 from that x power. So it gives me x to the power 1. So that thing goes there. And of course, 2 upon 4, I can just simplify to say a half, right? So I'll get rid of that. That guy is minus a half. Okay, then what is the product rule? Product rule is v du plus u dv, right? vu prime plus uv prime. Now, I memorized that in a different order to the way I suspect most of you learn. Most of you learn u dv plus v du, the other way around. But I remember it in this order because it's the same order as the quotient rule, which means that when I do the quotient rule, I'm less likely to make a mistake. Okay, let's substitute this in. So we've got e to the power negative a quarter x squared times by du, which is 1, plus u, which is x, times by minus a half x, e to the power negative a quarter x squared. And I think usually the best thing to do is want to factorize things out. So I can factorize out e to the minus a quarter x squared, and that's going to give me 1 there, and negative a half x squared there. Okay. Now we want to find where dy dx is equal to 0. So we're going to write something like this: stationary point when y prime is equal to 0. So I can set this whole thing equal to 0. E to the minus a quarter x squared times by 1 minus a half x squared there. Sorry, that was a bit messy, wasn't it? Let me just try to simplify that a little bit. And that means that I've got two things multiplied together that give me 0. So either this thing is equal to 0. Well, the exponential is never equal to 0, so that's not a solution. Or this thing here is equal to 0. So I'm going to set 1 minus a half x squared equals 0 as a solution. And therefore, a half x squared is equal to 1, which means that x squared is equal to 2, which means that x is equal to the square root of 2. Now, it could be plus or minus the square root of 2, but it's obviously got to be the positive value because the x coordinate here on the graph must be a positive, right? A negative value is going to be over there. We want to find the exact coordinates, so we need to substitute this into our y. So y, remember, is equal to x e to the negative a quarter x squared. Let me just make sure I've got that function right. Okay, so when x is equal to root 2, y is going to be equal to root 2 times by e to the minus a quarter root 2 squared, which is 2. And negative a quarter times by 2 is negative a half. So what we've got here is coordinate root 2 e to the power negative a half, and therefore the coordinate is root 2, comma, root 2 e to the power negative a half. Okay, part B of this question, using the substitution x is equal to root u or otherwise, find by integration the exact area of the shaded region bounded by the curve, the x-axis and the line x is equal to 3. Well, why don't we set this up first of all as an integration in terms of x. So the area is going to be equal to the integral of the curve, which is x e to the minus a quarter x squared dx. And it's between 0 and 3. Now, can I really encourage you, for those of you who are not used to writing dx here, please do that because it's actually very important when you come to do this kind of problem. I'm going to show you why just in a moment. Now, we are going to use the substitution as we're encouraged to do in the question. So let x equal root u, so it's u to the power of a half. And we're going to differentiate that. Okay, if we differentiate that, we get dx du is equal to a half u to the power minus a half. Now, how do we use substitutions? Basically, in the integral, every place we got an x, we're going to want to replace it with a u, but also every place we got a dx, we're going to want to replace it with a du. So what I'm going to do is I'm going to take this guy here, just rearrange him ever so slightly so that we get dx is equal to a half u to the power minus a half times by du. Now, what that's doing is it's kind of treating this guy like a fraction. It's not really a fraction, but it's kind of useful and convenient from our purposes. So what I'm going to do now is I'm going to rewrite my integral. The area is going to be the integral of x. Now, x is equal to u to the power of a half, right? So I replace the x with that. E to the power minus a quarter x squared. Well, if x is root u, then x squared is just going to be u. And then dx is going to be this whole thing here, right? So that is a half u to the power minus a half du. Now, what's the great thing about that? The great thing about that is that these two terms cancel each other out. Okay, so those are gone. And so therefore, I can rewrite this integral as a half the integral from e to the power negative a quarter u du, right? So that is a nice, easy integral that we can do. Now, you may have noticed so far, I haven't actually dealt with the bounds, right? Now, this is another tricky thing. This is x is equal to 0, and this is x is equal to 3. So what we need to do is if we've converted our integral from an integral in terms of x to an integral in terms of u, we also need to change those bounds. So when x is equal to 0, well, u is also going to be equal to 0. Okay, so that guy there is 0. But when x is equal to 3, then that means that root u is equal to 3. So if we square both sides, u will be equal to 9. So the upper boundary there changes to 9. Okay, so now we've got everything set up. We should just be able to integrate. So if I integrate this guy, I'm going to get a half e to the power minus a quarter u. And then what do we do? Well, we take the coefficient of the power. So we take the negative a quarter and we divide by negative a quarter. And dividing by negative a quarter is the same thing as timesing by negative 4. Okay, so that's how we integrate that term. And remember, we've got to have the boundaries there, 9 and 0. I think I'll just try to simplify this a little bit first. So that guy is going to be minus 2 e to the power minus a quarter u between 9 and 0. Okay, so if I substitute in the top bound, I'm going to get here minus 2 e to the power 9 upon 4. And if I substitute in the lower bound, I don't get 0. You need to be super careful about that. I get e to the power 0, and e to the power 0 is 1. So actually what I've got here is I've got minus 2 e to the power negative 9 upon 4 minus 2, which is plus 2. Okay, and so that guy there should be my answer. Okay, question 10. We've got a function here like that, and we want to express it in partial fractions. Now, the key thing to understand here is that we have got a repeated factor on the bottom, right? So we need to deal with that in a special way. So I'm going to write that as follows. We've got 24x plus 13, all divided through by 1 minus 2x times by 2 plus x to the power of 2. And so what are we going to get here? Well, we're going to get a term with 1 minus 2x as a denominator. We're going to get another term with 2 plus x as a denominator. And then we're going to get a third term with 2 plus x squared as a denominator. Okay, so this is basically the key thing you need to recognize. If I've got a term repeated on the denominator, then I need to have two separate fractions, right? So in this case, I need to have 2 plus x, but I also need to have 2 plus x all squared. Now, the way I'm going to deal with this is I'm going to combine all of these guys. So I've got to give them all a common denominator. If I give them all a common denominator, that means I need to times the first fraction by 2 plus x squared. So I get a bracket 2 plus x all squared. The second fraction, I need to multiply by 2 plus x and 1 minus 2x. Okay, like that. And then the third fraction, I need to multiply by 1 minus 2x. So I get there c bracket 1 minus 2x. And this is all over the common denominator, therefore, which is 1 minus 2x times by 2 plus x all squared, right? So that's going to be equal to 24x plus 13 over the same thing, which is 1 minus 2x, 2 plus x all squared. Now, if that's the case, we actually don't really need to consider the denominator anymore, right? Because they're both the same. All we need to do is to compare the numerator. So what I'm going to do is I'm just going to delete the denominators because I'm no longer bothered with those. Okay, and I'm going to be comparing the terms on the left-hand side of my identity and the right-hand side of my identity. And an efficient way of doing this, right, is we could compare the coefficients of x, right, on both sides, the constant term on both sides, and actually as well the coefficient of x squared on both sides. We can sort of imagine on the left-hand side we've got 0x squared, and on the right-hand side we're going to have some other expression. But I think elimination is a much more effective strategy in this case. Elimination is where we substitute in a particular value of x, and that value of x should make some of these terms disappear. So let's just think about that. If I was to substitute negative 2 into here, then this term is going to become 0, so that guy disappears, and this term becomes 0, so it means this guy disappears, and all we're going to be left with is the c term, right? So that's what I'm going to do. I'm going to substitute in x is equal to negative 2. Okay, now if I do that on the left-hand side, I'm going to get 24 times by negative 2, which is negative 48, plus 13. On the right-hand side, that guy is going to be 0, that guy is going to be 0, and I'm going to be left with this guy, which is c times by 1 minus 2 times minus 2, which is plus 4. So in other words, we've got 5c. Now let's simplify the left-hand side. Negative 48 plus 13 is negative 35, is equal to 5c. So c is equal to negative 7, right? So we got our c term. Well, is there another thing that we could substitute in? Well, let's consider this bracket here. If I was to substitute in x is a half, then we get 1 minus 1. That's going to become 0. Right? So that means that this whole thing would become 0 and that whole thing would become 0. So that would leave us with the a term. So that's what I'm going to do next. I'm going to substitute in x is equal to a half, because if I do that, on the left-hand side, I'm going to get 24 times by a half, which is 12. So I'm going to get 12 plus 13. Okay. And then what did I say? This bracket will become 0, and this bracket will become 0. So these two whole terms disappear, and I'm left with 2 plus a half squared times by a. Now, 2 plus a half is 5 upon 2, so we've got a times by 5 upon 2 all squared. So let's simplify this. So firstly, 12 plus 13 is 25, and that's going to be equal to a times by 25 upon 4, and so therefore a is going to be equal to 4. Okay, so we've got A, we've got C. So now what we need to do is we need to find B. Well, our elimination strategy no longer works. So what could we do instead? Well, I suggest that what you do is you now compare the constants on both sides. So the constant on the left-hand side is going to be 13. Is there a clever way we can get the constant on the right-hand side without having to expand all of this? Well, there is. Because if I was to square this bracket out, the constant term is going to be 2 squared is 4. These brackets, if I square them out, if I expand them rather, I'm going to get 2 times by 1, which is just 2. And with this bracket here, I'm just going to get 1 times by c. Okay, so in other words, 13 should be equal to 4a plus 2b plus c. So that's what I'm going to write. Sorry. So comparing the constants, on the left-hand side, I've got 13 is equal to, I think, was it 4a plus 2b plus c. Okay, and a we said was 4, so 4 times by 4 is 16. B is the thing we're trying to find out, that's 2b. And c, what was c? Negative 7. So we've got minus 7 there, is equal to 13. So 2b, well, I'll add 7 to both sides, so I get 20, and then subtract 16, that gives me 4. So b should be equal to 2. So I get a is 4, b is 2, c is negative 7. So if I was to put them in here, so can I copy that? Probably some way of doing that. Never mind. I'll just write it out again in full. So our fraction, I'll do it up here, save a bit of space. Our a was 4, so it's going to be 4 upon 1 minus 2x plus 2 upon 2 plus x, and then minus 7 upon 2 plus x all squared. Okay, so there we go. We expressed it in partial fractions. I'm just going to check my answer, see if I've got that guy right. Make sure. Let's get down. Yeah, exactly right. All right, then, so here we are in part B. Part B is hence obtain an expression for f of x in ascending powers of x up to and including the term in x squared. Okay, so what's this about? Well, basically, we've got to use our binomial expansion to expand each of these terms here. Now, these kind of questions, I think really actually they're quite simple in a way. You just follow the formula, but they can be long, they can be tedious, and there's lots of room for mistakes. So I think you just need to be a little bit methodical. Now, this guy here, we can write the fraction as being 4 times by 1 minus 2x to the power of negative 1. Okay, but I don't want to get too confused at the moment, so I'm just going to ignore that 4. I'm just going to expand the bracket terms here. Now, the formula, for those of you who are a little bit uncertain, if I've got 1 plus x to the power of n, where n is not a positive integer, then the way that I expand this is I get 1 plus nx plus n minus 1 x squared upon 2 factorial plus n bracket n minus 1 n minus 2 upon 3 factorial x cubed, and so on and so on and so forth. Now, actually, these guys here, you can think of it as divided by 1 factorial, and this guy divided by 0 factorial. So the pattern still basically holds. And in this case, what do we want? Well, we only want the first three terms. We only want that guy there. Okay, so I can get rid of these. Not really important. Okay, we want to do this for each of the terms. Now, a slight caveat of that. This only works if the term here is a 1, right? So, for example, where we've got 2 plus x, we're going to need to change that so that that's a 1. And the other thing is this expansion is only valid for a certain set of values, and that's going to be when this x value here is between 1 and -1. So we sometimes have to explain that. But at the moment, what we'll do is we're just going to expand that 1 minus 2x to the power of -1 using the same formula I've just done. So 1 minus 2x to the power of -1. Did I get that right? 1 minus 2x? Yeah. Okay, so what's that going to be? That's going to be equal to 1 plus n is minus 1 times by x. Well, x in this case is the -2x, right? Because if you want, we can think of this as like being plus minus 2x. Plus n, which is -1, times by n minus 1, which is -2, all over 2 factorial, which is 2, times by x squared. Okay, and what's our x squared here? It is -2x all squared, right? So perhaps if I want to just make that super clear, I'm just going to change that thing there. I'm treating this as 1 plus minus 2x all expanded, right? So in this expansion where I've got x, right? So I've got x there. This would be nx. Sorry, my pen's not working. And this is x squared. Then here it's replaced with -2x, right? So I've got -2x there and a -2x squared there. All right. Now what I'm going to do is I'm going to simplify this. So I'm going to get 1. -1 times -2 is +2, so +2x. I've got -1 times -2, which is 2, divided by 2 is 1. And then -2x squared is plus 4x squared, right? So, and then plus ... We're not interested in all the other terms. Okay, so that's the first thing. Then what I want to do is I want to expand 1 upon 2 plus x. So I want to expand 2 plus x to the power of -1. But remember what I said a moment ago, this term here, that guy, that needs to be a 1. So the way I'm going to do that is I'm going to factorize out the 2. So I'm going to get 1 plus x upon 2, like that, to the power of -1. And if I do that, that's like having 2 to the power of -1 times by 1 plus x upon 2 to the power of -1. And then that guy I can expand, right? Because the term here is a 1. And of course, 2 to the power of -1 can be rewritten as a half. So I'm going to write that as a half like that. Now, if I expand this whole thing, what am I going to get? Well, using our formula, we're going to get 1 plus nx, so that's -1 times by x upon 2, plus n, which is -1, times by n minus 1, which is -2, all upon 2 factorial, times by our x squared, which is x upon 2 all squared, plus ... Okay? Once I've got that, I can simplify. This is a half bracket 1 minus a half x. -1 times -2 is +2, divided by 2 is 1. And then x upon 2 squared is plus x squared upon 4, plus ... And so this thing simplifies to give a half minus a quarter x squared plus an eighth x, not x squared there, beg your pardon, minus a half a quarter x, plus an eighth x squared plus ... All right, that's all that. Then the last term we've got to expand is the 2 plus x to the power of -2, right? We've got to expand this guy here. Okay, so let's do all of that. So we've got 2 plus x to the power of -2. Again, we've got to deal with that 2 at the front. So I'm going to write that as 2 bracket 1 plus x upon 2, all to the power of -2. And that's the same thing as 2 to the power of -2 times by 1 plus x upon 2 to the power of -2. And if I do that, 2 to the power of -2, that is a quarter, because it's the same thing as 1 upon 2 squared. And now I'm going to expand this whole thing here. So I'm going to get 1 plus n, which is now negative 2, times by x, which is x upon 2, plus n, which is negative 2, n minus 1, which is negative 3, upon 2 factorial, which is 2, times by the x upon 2 all squared. Okay, plus dot, 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 if you prefer. Now, if I simplify this, I'm going to get a 1 here. That's going to become minus x because the 2's cancel out. I've got negative 2 times by negative 3 is positive 6, divided by 2 is positive 3, and then x upon 2 all squared is x squared upon 4. Okay, and then I will expand this. I get a quarter minus a quarter x plus 3/16 x squared plus dot, dot, dot. All right, now then, all of this we've got to piece together. So we are going to have f of x is 4 times by the expansion of this, plus 2 times by the expansion of that, plus minus 7 times by the expansion of that. So let's write that all down. So I'm going to move over here. F of x is going to equal to 4 times by the first expansion, which was 1 plus 2x plus 4x squared. Okay, so 1 plus 2x plus 4x squared. Okay, 1 plus 2x plus 4x squared. Yep. And then plus 2 times by the other expansion, which is that, isn't it? A half minus a quarter x plus an eighth x squared. So what was it? Sorry about the moving around. So plus 2 times by, I think it was a half minus a quarter x plus an eighth. Half minus a quarter plus an eighth. Okay, sorry. So a half minus a quarter x plus an eighth x squared. And then the last one was minus 7 times by the last expansion. If I go all the way down to the bottom, which was a quarter minus a quarter x plus 3/16. So a quarter minus a quarter 3/16. Okay, let's go up. So a quarter minus a quarter x plus 3/16 x squared. Okay. Sorry, just double check that one more time. I know it's just you'd be so careful with these because you can make small errors and they're really annoying. Okay. All right. So now I think all I've got to do is just got to expand this whole thing. So I'm going to get 4 plus 8x plus 16x squared plus 1 minus a half x plus a quarter x squared minus 7 quarters plus 7 quarters x minus 21/16 x squared. Okay, so let's add up all the constant terms. We've got 4 plus 1 is 5 minus 7 upon 4. So 5 is 20 quarters, that's 13 quarters. Okay, 8x minus a half x plus 7 upon 4. So that's 32 upon 4 minus 2 upon 4 is 30 upon 4. And plus that is 37 upon 4. And then we've got 16x squared plus a quarter. So that's 65 minus, and that is 239 upon 16 x squared. Okay, and that's our answer. Okay, then part C of this question, we want to state the values of x for which the expansion is valid. Now, I think I mentioned this a little bit earlier. When we do these kind of expansions, okay, this term here needs to be between 1 and negative 1. So let me just go up, go to the general thing. That x there needs to be between 1 and negative 1. So in each of our expansions, we've had negative 2x, we've had we've had x upon 2, beg your pardon, and we've had, again, x upon 2. So each of those things needs to be between 1 and negative 1. So I'll rewrite that. So we go down here. So we had negative 2x. That needs to be between 1 and negative 1. Well, another way of writing that is that the modulus of negative 2x needs to be less than 1. And also we want to have the modulus of x upon 2 to be less than 1. Okay, well, if we do that, then that means that the modulus of x must be less than a half if we just kind of divide both sides by 2. The negative is already dealt with by the modulus, right? It just turns into a positive. And here we would need to have that the modulus of x will be less than 2. Now, of course, if the modulus of x is less than a half, then it's also going to be less than 2. So actually, we don't need this guy anymore. We can sort of basically just cross him out. And we can say that the only condition is the modulus of x must be less than a half. Okay, then question 11, which is a vectors question. I think I'm going to deal with parts A and B here together. So in this diagram, we've got a cuboid in which OA is a length of 3 units. So I think I'm going to label that on, right? That length there is 3. And the length OC, which is this guy here, is a length of 2 units. So again, I'm going to label that. That's a length of 2. And OD is also equal to 2 units, right? So that length there is also equal to 2, which is the same as AE. So I'm going to label that there as 2. Okay, the unit vectors I, j, and k are parallel. So we've got I, j, k in the usual configuration, right? Make sure you don't mix them up. And m is the midpoint of EF. We want to find the position vector of m. Well, how do we get to m? We move 3 in that direction, so 3 in the I direction. We're going to move 2 in the j direction, right? So that's the j direction there. And then we're going to move up in the k direction. Now, how far do we go? Well, we don't go up to the full length. We go a half of that, which is 1. So we can say that the position vector of m, which I'll write OM, is going to be equal to 3 in the I direction, 2 in the j direction, and then 1 in the k direction. So 3, 2, 1. I prefer to write it as column vectors, but if you want to write it as I, j, and k, that's 3i plus 2j plus 1k. Okay, so that's that. Okay, then next thing we want to do is we want to calculate the angle PAM. So what's PAM going to be? Well, instead of using the diagram here, I think what I'm going to do is just draw out 3 points, right? Let's say I've got like this and that. Okay, so it doesn't have to represent the diagram. Let's say that's the point P, that's the point A, and that's the point M. Right, then the angle PAM is that angle there, right? So for simplicity, I think I'm just going to label that angle there as theta. Now, how do I find the angle there? Well, I can use a vector relationship, because if I find the scalar product of the vector AP with the vector AM, then I can exploit the following formula, because I know that AP scalar producted or dot producted with AM is going to equal to the magnitude of AP times by the magnitude of AM times by the cosine of the angle between them, right? So hopefully that should be a formula that you're quite familiar with, right? So if I want to find the angle between any two vectors, in this case AM and AP, then the scalar product of those vectors is going to be equal to the size of this times by the size of that times by the cosine of the angle between them. Okay, so in order to do this, first thing that I need to do is I need to find the vector AP, and I need to find the vector AM. Well, I think we should just start by writing these things down, right? So firstly, the vector O to A, right, if I write it in column notation, is going to be 3i and 0j and 0k. So it's 300. So I'm going to write that down. So the vector OA is 300. What was the vector of position vector of OM? Well, we calculated it just a moment ago. That was 3, 2, 1. So I'll write that down there. This is 3, 2, 1. And what's the position vector of P? Well, we're given it in the question. We are told that P is 1, 1, 2. So I plus j plus 2k. So 1, 1, 2. Now, what do I want to find? Firstly, I want to find the vector AP. So the vector that takes me from A to P can be found by doing OP minus OA, right? So hopefully you should be familiar with this by now, right? If I want a vector that goes from A to P, then that's going to be the same as the position vector of P minus the position vector of A. Okay, so in this case, what I'm going to get is the vector 1, 1, 2 minus the vector 3, 0, 0. And if I get that, I'm going to get negative 2, 1, 2. So that's the vector AP. Then if I want to get the vector AM, then that's going to be the same thing, right? I need to do OM minus OA. And OM is 3, 2, 1, and OA is 3, 0, 0. So if I calculate that, I'm going to get O, 2, 1. And by the way, guys, I hope you can notice the ease of using the column vector notation instead of the IJK, right? Column vectors, I did a degree in engineering, right? And basically everyone uses column vectors. I really can't remember a time when I used IJ and K, because just IJ and K makes things so much harder to actually see and to practically do. So I suggest you use columns because I think it is just easier. Okay, then what do I need to do next? Well, I need to find the scalar product of these two, right? So AP dotted with AM is negative 2, 1, 2 dotted with 0, 2, 1. How do I do the scalar product? Well, I take the I components and I multiply them. So negative 2 times by 0 is 0. So I get 0 there. Plus what the J components multiplied. So 1 times by 2 is 2. Plus the K components multiplied. So 2 times by 1 is 2. So 0 plus 2 plus 2 is 4. So I get that. And then I need to find the magnitude of each of these vectors. So the magnitude of AP is going to be equal to the square root of negative 2 squared plus 1 squared plus 2 squared. And so that's going to be equal to 4 plus 1, which is 5, plus 4 again, which is 9. And the square root of 9 is 3. So that's that. And we can do the same thing for the magnitude of AM. If I do that, I'm going to get the square root of 0 squared plus 2 squared plus 1 squared. So 2 squared is 4 plus 1 is 5, so that's the square root of 5. And now all I've got to do is just got to substitute them into the formula. So the scalar product of the two vectors is 4 is equal to the magnitude of AP 3 times by the magnitude of AM, which is root 5, times by the cosine of the angle between them. And so therefore, cos theta is going to be equal to 4 divided by 3 root 5. And theta is going to be equal to the cos inverse of that, 4 upon 3 root 5. Well, this is where we need to get out our calculators, and hopefully you should be able to get an answer. Okay, and I get 53.4 degrees, which is our answer. Okay, here we are in part C. We want to find the exact length of the perpendicular from point P to the line passing through O and M. Now, I think in this particular question, the diagram given is probably not going to help you so much, but you should definitely draw your own diagram that has all the important points, right? Remember, vectors are visual things, and so diagrams really help you to understand them. Now, what is being described here? Well, imagine we've got a line OM, right? That's that blue line there. And we've got this point P here that's somewhere in space. Well, what we want to do is we want to find the perpendicular line that takes us from P to that line, that blue line there. In other words, what we're trying to do is we're trying to find the shortest distance from the point P to the line OM. Now, if you're doing further maths, there's actually a much faster way that you can do this using the vector product or the cross product. But I'm assuming that people are not doing further maths, and so we need a method that you understand. And so this is what I'm going to encourage you to think. If we've got these two lines, the blue line and the green line, these lines are perpendicular. That means we've got two perpendicular vectors, right? We've got the vector OM, which is our blue line, that guy there, is going to be perpendicular to that green line. Now, I should probably give this point here on the line OM a name. Now, in the mark scheme, they give it the letter Q, so I'm also going to call it Q to avoid confusion. And so what I'm saying is that the vector OM is going to be perpendicular to the vector PQ. Now, why is that helpful? Well, because we know that if two vectors are perpendicular, their scalar product is going to be 0. So if we can find an expression for PQ, we know that the scalar product of PQ with the vector OM will be equal to 0. Right? So let's try to figure that out. So firstly, what we need to do is we need to find what OQ is. Well, OQ is just a fraction of the distance along the line OM. Right? So OQ is some distance along that line OM. We just don't know what it is. So we're going to call that constant there lambda. So we can write OQ as lambda times by OM, which is therefore lambda times by 3, 2, 1. Well, if that's the case, then we can find the vector PQ. Because what will PQ be? PQ will be the vector OQ minus the vector OP. And OQ, we've said, is 3 lambda, 2 lambda, 1 lambda, minus OP, which is 1, 1, 2. 1, 1, 2. So if we were to kind of put that all together, that's going to be 3 lambda minus 1, 2 lambda minus 1, and lambda minus 2. That's the vector PQ. PQ. And we know that if we scalar product that with the vector OM, which is 3, 2, 1, so OM, I'll just write it over here again, is equal to 3, 2, 1, then we know that the scalar product of OM with PQ, right, so PQ is that vector, must be equal to 0. So how are we going to find the scalar product of these two? Well, we're going to do 3 times by that. So that's going to give me 9 lambda minus 3 plus 2 times by that. So it's going to give me 4 lambda minus 2. So 4 lambda minus 2 there. Plus this, this times by that. So it's going to be lambda minus 2. Okay, and I think if I combine all those, well, 9 lambda plus 4 lambda is 13 lambda, plus lambda is 14 lambda. Sorry about that, it's a bit messy there. Let me just tidy it up. 14 lambda. And we've got 3 plus 2 plus 2 is 7. So lambda is equal to a half, right? So actually, that point Q there is the midpoint. So if that's the case, then we can find out what the vector PQ is. Let's just go over here. Right, so if lambda is equal to a half, then the vector PQ is going to equal to 3 times by a half, which is 1.5 minus 1, so that's just a half. 2 times by a half, which is 1 minus 1 is 0, and then a half minus 2, which is minus 3 upon 2. So that's our vector PQ, right? So we've now found on our diagram the green thing. And what do we want? We want to find the exact length. Well, how are we going to find the exact length? We just got to find the magnitude of that guy. So we find the magnitude of PQ, and the magnitude of PQ is going to equal to the square root of a half squared, which is a quarter, plus 0 squared, which is 0, plus negative 3 upon 2 squared, which is 9 upon 4. And if we do that, that's going to be 10 upon 4 square rooted, which is the same thing as the square root of 10 upon 2. And that should be our answer.